Hello, I'm Jin Kim from Mobile Network and Communication Lab. Let me start the presentation to review the paper for Quantum Machine Learning for 6G Communication Networks, State of Art and Vision for the Future. Before the presentation, I would like to describe the abstract of this paper to help the understanding. The vision for 6G is a massively connected complex network capable of rapidly responding to the user's service calls through real-time learning of the network state as described by the network edge. Then the multi-state, multi-dimensional nature of the network state, requiring the real-time knowledge can be viewed as a quantum uncertainty problem. In this regard, the emerging paradigm of machine learning, deep learning, quantum computing, and quantum machine learning and their synergies with communication networks can be considered as core 6G enablers. In this paper, a comprehensive review of the related state of the art in the domain of ML, DL, QC, and QML and future research direction for 6G communication networks. This presentation will proceed in the following steps. First, I explain why we should consider beyond the 5G network to introduce the motivation of 6G network. And next, I'll describe the basis of machine learning and deep learning and quantum computing to understand the concept of quantum machine learning. Based on this, I will introduce the future research directions and conclusion. The global mobile data traffic is forecasted to grow 55% annually between 2020 and 2030. To support this, the 6G networks are widely projected to provide larger volumetric spectrum and energy efficiency relative to the 5G networks, and they will have a very complex structure incurred from massive connectivity. This tremendous amount of data may be harnessed with strong processing and learning capabilities to manage the network at different levels. To this end, we can consider machine learning and quantum computing methods as a significant enabler. While 5G networks have introduced many technology innovations, the network's stringent performance requirements have also raised new design considerations. The required considerations are throughput, network capacity, energy efficiency, backhaul and access network congestion, and data security, so on. They may be addressed by some emerging technologies that can feature in the evolution towards 6G communication networks. First of all, machine learning is a new representative technology currently being considered in 6G communication network. The deployment of ML in communications is to build self-sustaining and adaptive networks capable to meet the dynamic reconfigurability demands of the future devices and services. We have several machine learning techniques in this regard, which I will discuss in turn in the next chapter. In supervised learning, annotated training data is available, and the coefficients of intermediate states are learned by exploding the prior available set of inputs paired with their corresponding desired outputs. And this supervised learning is typically used for the classification and regression nature problems. In semi-supervised learning, a small amount of annotated training data is available while most of the data is unlabeled. Whereas no annotated training data is available in unsupervised learning. Semi and unsupervised learning is typically used for clustering and classification natured problems. Reinforcement learning is realized on the basis of a feedback performance indicator conceived from the environment after computing a specific output for a specific observation by adaptively converging to the ideal behavior through maximization of the reward. Typically, reinforcement learning is used for control and classification problems. And genetic algorithms are among widely explored methods for resolving various optimization and estimation problems at different layers of communication systems. Genetic programming evolutionarily evaluates the fitness of objectives given the constraints and limitations to find an optimal solution to the subject problem. Additionally, we need to understand the full concept of artificial neural network for machine learning. ANN is a biologically inspired data processing structure which is designed to learn different operations from the observed data. ANNs are generally used to recognize any patterns within the input data by passing the data through different layers of simulated neural connections. An ANN is composed of connected input, hidden, and output layers of neurons, where each node performs combining and/or limiting operations and each connection performs scaling operations. Then, training of ANNs is the process in which the weights of the connections between the neurons are learned. The training of ANNs is usually performed in a supervised learning fashion, where the prior available data labeled with the desired output is exploited to compute the error for adjustment in weights. ANN have been deployed to perform and assist in various operations of communication systems, such as for decoding for MIMO FDM systems or an ANN-based method for predicting channel features for large-scale multi-antennas base stations. Especially, we need to understand the concept of deep learning with respect to machine learning. First, DL is a sub-branch of ML in which the system intelligence is learned through the propagation of input data in massively connected multiple layers of the system. And a DL system automatically learns to model the high-level abstractions in the given data by extracting important features from it. In the next chapter, we will look at several methods related to deep learning for communications. Regarding DNN, the DNN can be considered as a typical example of DL, which is an ANN containing a high number of hidden layers of neurons and a complex structure of connections between the neurons. The DNN has enabled its deployment in even delay critical applications, which is achieved through offline training the DNNs and then performing the online operations. Regarding deep transfer learning is another new direction of research to reduce the dependence of learning from the required large amount of data. This learning technique offers the advantage of facilitating the learning process by reducing the amount of required data and relaxes the condition on the training data to be independently and identically distributed with the validation data. Regarding the unfolding concepts can be used to unfold a neural network for each iteration of the iterative algorithm into a layered structure and then unite it together to come up with the optimum ANN architecture that can be easily trained for the given problem. Regarding deep learning for cognitive communications, cognitive radio techniques enables a radio system to sense, learn, and adapt based on the context of the surrounding environment. The sensing, learning, and adaptation may allude to the sensing of radio spectrum, user demands, and spatial environment. We need to go one step further and understand the quantum technology and QML-assisted communication. QC and ML can create close synergies with each other towards providing their joint benefits in communication systems. This concept of parallelism comes from quantum physics concept of qubit, entanglement, and superposition. A qubit can simultaneously hold both and binary states 0 and 1. Subsequently, any n interacting qubits can simultaneously represent two n unique binary patterns, which is unlike a single binary pattern and once in the classical computers. These quantum mechanic concepts are well recognized for generating counterintuitive statistical data patterns, which classical computers are unable to produce effectively. Also, it is envisioned that the combination of QC and ML features together in the framework of QML can produce and recognize the statistical data patterns which classical computers and classical machine learning are unable to perform effectively. Quantum communication is the emerging branch of telecommunications engineering, which has been motivated from the principles of quantum mechanics and is based on the exchange of quantum states. The novel field of research area aims to utilize the quantum theories principles to enhance the capacity of future communication systems as well as to incorporate new functionalities. Quantum-assisted communication can enhance various aspects of the existing classical communication networks, including channel estimation, optimal voltage detection, the design of optimal pre-coding metrics, and the optimal routing by employing the quantum algorithm. One important advantage of utilizing quantum domain in communications is high degrees of freedom. In the communications and computing domains, the existing protocols can be enhanced with more efficient algorithms by the utilization of quantum principles and tools. In summary, quantum principles provide significant benefits to the communication networks, such as enhanced channel capacity, the ability to transmit unknown quantum states, and to deliver secure information by utilizing a number of advanced communication protocols. Based on the previous mentioned concept for machine learning, deep learning, and quantum communication, the machine learning methods can be revisited in the context of quantum-assisted algorithms for ML and the QML framework. Quantum principles based on emerging computing technologies will bring entirely new modes of information processing. When quantum computing is applied to existing machine learning methods, it has the following characteristics. In supervised and unsupervised QML algorithms can provide exponential speed-ups over classical ML algorithms involving large dimensional data in both supervised and unsupervised learning approaches. Alongside, QML can also enhance security and privacy in communication networks. In quantum reinforcement learning, quantum speed-up for reinforced learning is an emerging framework with a strong potential in the agent environment paradigm. For this, some fundamental characterization to study performance trade-off between exploration and exploitation of quantum parallelism for speeding up reinforcement learning is conducted. In quantum ANNs, spreading the fundamental concepts of quantum information processing and ANNs, a QNN concept has been introduced. But among various difficulties in realized QNN, the maintenance of coherence during quantum parallel distributed processing and implementation of interconnections between neurons in the form of entanglement of qubits are the most notable. In quantum deep learning, the derivation of DL models for simulating complex neural topologies and data flow mechanisms is not naturally supported by the classical computing architectures. In this regarding, quantum computing-based algorithms for DL are envisioned to have a profound impact on the evolution of ML methods. And quantum DL algorithms can not only outperform conventional learning algorithms in terms of processing time, but also in terms of enrichment in modeling quality. Lastly, I would like to summarize the future research direction introduced in this paper. First, the increasing size, complexity, services, and performance demands of the communication networks necessitate a deliberation for envisioning new technologies for enabling and harmonizing the future heterogeneous networks. Second, overwhelming interest in AI methods is seen in recent years, which has motivated the provision of essential intelligence to 5G networks. However, this provision is only limited to perform different isolated tasks of optimization, control, and management nature. Third, the recent success of quantum assisted and data-driven learning methods in communication networks has a clear motivation to consider these as enablers of future heterogeneous networks. In conclusion, a comprehensive review of the emerging technologies, including ML, QC, and QML, and put forward our vision for QC and QML assisted framework is provided in this paper. And the state of the art of quantum, QC assisted, ML assisted, QC assisted ML, and QML assisted communications have been thoroughly reviewed. Furthermore, a QC-assisted ML and QML-based framework for 60 communication networks has been proposed and future research directions were suggested. This is the end of my presentation. Thank you for listening.